All right, so here is the final case of a free-falling object that's thrown up in the air, but this is non-symmetric free fall. So this is going to be a little bit different than the last symmetric free fall problem. Some assumptions we can't make. So picture yourself like on top of a building. You throw something up in the air and then it falls down to the ground, or vice versa, right? You're on the ground, you throw something up in the air, and it lands on the top of some building, something like that. So those cases where you're throwing something up in the air, but the object's final position is different from its initial position. That's this case, non-symmetric free fall. So we want to divide it up into parts if necessary, but sometimes we'll have enough information to where the kinematics equations will kind of do the work for us, and we don't really have to split it up into the part where the object is ascending and the part where the object is descending. But sometimes we'll have to, so we'll look for that. This student is throwing a ball up in the air, so we've got a positive initial velocity, 15 meters per second. The ball is 2 meters above the ground. So this student is 2 meters above the ground, throws a ball up in the air, it lands on the ground. So we're looking for total hang time again. How long is the ball in the air? And we'll see there are going to be a couple different things that we can find along the way while we find this time. So that'll be good practice. So object and the student are on top of the cliff or whatever platform they're on. Initial velocity of positive 15 meters per second. It does reach a max height, right? That's when the velocity is 0. So we're not being asked for it, but again, it might be helpful to find H max. But this part right here would be very similar to the previous problem, right? If we're just looking for the max height, we don't care about the descent of the object, right? So how far it falls. So this problem right here can be solved like the last problem, finding H max. So we're looking for the total time. So this looks nice, right? Because it's got everything. We've got the displacement. Notice that the displacement again in this case is negative 2 meters. The object starts at a position of 2 meters and it lands on the ground. Again, I'm picking the lowest point to be y equals 0, right? So the ground below this this platform is going to be y equals 0, and then the height of this platform is positive 2 meters. Calculate delta y, you get a displacement of negative 2 meters. So I've got everything I need here to solve for t. What I don't like is it's a quadratic, and I don't have any terms that go away. So, and it's not a very nice. So I'm kind of cheating here a little bit. I'm substituting the numbers in first. All right. Usually that's a big no-no. I really don't like to do that, but I'm doing that here. I'm going to drop my units, and I'm just going to simplify these constants. And I see this quadratic, right? I see this parabolic function, which makes sense, right? Position is a function of time, and this is a parabola, right? So I got to use a quadratic formula. Can't stand the quadratic formula, but sometimes it comes back to haunt us. So I put it all together, right? I substitute everything. I sing my little song, whatever, Google, cheat, look up quadratic formula. And I get these two roots, right? So I'm solving for time. I get these two roots. I get positive 3.2 and negative 0.13. All right. Maybe we'll stumble across the significance of this negative 0.13 in the future. But for now, I'm just going to cross it out because it's negative. I know time has to be positive because it's a scalar. So I'm going to pick 3.2 seconds. Right? Problem's done. That's great. But again, I like to avoid the quadratic formula whenever possible. If you got a calculator that does it for you, great. That's pretty straightforward, right? I got lucky. I got all the variables, quantities for variables I was looking for. It was just missing time, so this worked out. Or and you may, if it's like a WebAssign problem or something, WebAssign problem might have a couple different parts to it. They may ask you for the speed of the object when it hits the ground. Right? We're not being asked for that, but this option is actually going to solve for a couple things. We're going to solve for what I'm calling V3 first. V2 is just this velocity up here when it's at max height. So I like to kind of switch my subscripts to numbers, right? If I'm dealing with more than one velocity. In the next problem, we'll see that's really useful. So I'm looking for V3, the speed that the object hits the ground, and I have enough information to use this, right? I've got the initial velocity of the object, I've got the acceleration, note the negative sign thing that I do, and I've got the displacement. So take the square root of both sides. I'm looking for V3. Again, I'm expecting it to be negative, okay? So just the mathematical purist side of me, I'm just making sure I'm putting the two roots, right? And I know I'm going to pick the negative one because the final velocity is in the negative y direction. Substitute my values, my units, and don't forget displacement is negative, right? So this is a positive number, and I get 16.25 meters per second in the negative y direction. Now the reason I did this first may seem like a lot of work to avoid the quadratic, but to me it's worth it. So I found V3 first, right? So in the event that I'm asked for the final velocity, I have it. Now that I have the final velocity, I can use this kinematics equation, right? Because I've got initial, final velocity, acceleration. I just need total time. So I didn't have to split this problem up into multiple parts, right? Because these equations are just doing everything for me, right? So I have the final velocity, the initial velocity. I can solve for time. Do my algebra, subtract the initial, divide both sides by negative g. I've got a nice expression for the total time. Substitute everything in. Don't forget your initial velocity, or your final velocity, excuse me, V3 is negative minus a positive initial velocity. Negative sign on the top, negative g down on the bottom. I get a positive hang time. Total hang time at 3.2 seconds. Same thing I got here. All right. So pick your poison, so to speak, right? You want to deal with the quadratic, or you want to deal with solving two equations, right? It's really up to you, but we end up with the same result. All right, so this is an example of an object that's in free fall, but not the entire time it's in the air. So we think about a rocket, right? A rocket has to be launched, right? So it's got to burn fuel. The fuel applies a force on the rocket, so there's an acceleration in the positive y direction, right? As it's launched, there's an acceleration in the positive y direction. It does start from rest on the ground, but there's a force, and we'll talk about forces in chapter 4. There's a force that's causing the rocket's velocity to change in the positive y direction. So it's not in free fall, it's subject to another force. So that first part we're going to treat like a kinematics equation or a kinematics problem in the y direction. We're going to treat that separately from, let's say, when the rocket descends or runs out of fuel or something like that. So there's a part of the problem where the object is not in free fall, and then another part where the object is in free fall. So we're going to split those up into different parts and then just solve them separately. So this rocket has an initial acceleration as it's being launched. It's got an initial acceleration of 10 meters per second squared. Again, I'm going to say because we're launching it, it's going to start at rest from the ground. So after 10 seconds, it runs out of fuel. So it has this acceleration, positive 10 meters per second squared. It has that acceleration for 10 seconds. So then it runs out of fuel. So there's no longer the force of thrust causing it to accelerate in the positive y direction. After those 10 seconds, the rocket's in free fall. So we picture a rocket, if we launched it and it ran out of fuel, it would continue to ascend for some time, it would reach its max height, and then it would fall down to the ground. So we're going to split that up. We're looking for the max height of the rocket, and then we're looking for, again, the total hang time, the total time the rocket's in the air. Now you're thinking to yourself, this has like this is symmetric, right? Sorry, that's what I was thinking about. This is symmetric, right? Because the rocket starts in the air and then the rocket lands, or it starts on the ground and then ends on the ground. But it's not in free fall the whole time. So it's not following a parabolic function of motion. Okay, so these are two different types of motion, so we can't treat it like a symmetric free fall problem. So we're going to split it up. We're going to talk about the first segment, right? The first part of motion where the rocket's not in free fall. So that lasts for 10 seconds. Okay, so first segment, I'm going to call the time of the first segment T1. And then I'm going to call the acceleration while the rocket's fuel is burning A1. Okay, now that's positive. Again, we're going to say it launches from rest, so I'm going to give that a V naught, okay, a V sub 0. That's going to be the very initial velocity when the rocket is launched. So in order to find the rocket's max height, we have to find how far it travels while the fuel is burning, and then how far it travels without fuel until it comes to rest again, right? Because we're looking for max height. So it's going to do this for 10 seconds, then it's going to be in free fall for some amount of time, I don't know, but it's going to have a displacement y2. We're going to add those two displacements together, and that's the max height. So I don't know what the velocity or the displacement of the rocket are the instant it runs out of fuel after these first 10 seconds. So I'm looking for what I'm going to call V1. V1 is going to be the velocity of the rocket the instant it runs out of fuel. Delta Y1 is going to be how far it travels in the Y direction. So I've got an acceleration, I've got a time, I've got an initial velocity of 0. So I'm going to use this kinematics equation. V final is V initial plus AT to solve for V1. Not in free fall, so this is going to be just the acceleration due to the rocket fuel. 0 for the initial velocity, positive 10 meters per second squared. For acceleration, 10 seconds for time. I've got a velocity of 100 meters per second. So as soon as the rocket runs out of fuel, it's got a velocity of 100 meters per second in the positive y direction. Now, I can treat this problem, once I find this displacement, I can treat this problem like it's the student throwing the object up in the air and then having it land down on the ground below the student. Okay, so once this stuff happens, this rocket is behaving just like that. You throwing something up in the air from a window and then it landing on the sidewalk. So let's find the displacement now that I have the total time, right? Now that I have the total time, still have the initial velocity of 0. I'm going to use this equation right here to solve for the displacement while the fuel is burning. Okay, that term goes to 0. I've got 1/2 times the acceleration times the time. Don't forget to square that. Okay, that gets lost along the way sometimes. 1/2 AT squared. I get a total displacement of 500 meters. So it's got a velocity of 100 meters per second, and it's 500 meters in the air after the rocket fuel burns out. Okay, so it's still traveling with a speed of 100 meters per second, and it's this high off the ground. Rocket fuel burns out. So now it's in free fall. So what I want to do is I'm looking for max height. Right? So I want to see how far it goes until it reaches a velocity of 0 again. Right? Because it's got this V1 of 100 meters per second. It's got this V1. So now I'm looking for a V2. I'm going to call it V2 is 0 meters per second. So when it gets to its max height, it's going to have a velocity of 0 meters per second. I'm looking for how far it travels. Now it's in free fall. We don't have any fuel. It's in free fall. That's the acceleration. So here's my equation, right? The final velocity, right? The velocity at max height is 0. The initial velocity, I know, it's 100 meters per second. Acceleration is due to gravity, g, negative sign. Looking for this right here, the second interval of displacement. That's a 0. Subtract the initial squared from both sides. Divide both sides by the negative sign, 2 and g. These negative signs are going to go away. Remember, that negative sign is not contained inside this v1 term. Okay, so I got v1 squared over 2g. I know all those terms, plug them in, and I get a second displacement of 510.2 meters. So max height is the sum of the displacement when it was ascending under the force due to the rocket fuel. The 510.2 meters is its ascent while it was in free fall. Add those two terms together, and then I've got a max height. So now I want the total time, right? I want the total time the rocket is in the air. I already know that the rocket is in the air for the first 10 seconds burning fuel. So if I just find the total time that the rocket is in free fall after it runs out of fuel, if I find that time, add it to the initial 10 seconds that the rocket was ascending and burning fuel, I've got the total time that the rocket was in the air. Okay. So again, I've got some options here. First option is I have all the information I need to solve this quadratic, because the total displacement of the rocket while it's in free fall is negative 500 meters. Okay, it starts off in free fall and it's 500 meters above the ground, right? So it goes up and then it comes back down, right? Over here, this is a better picture. It goes up, reaches max height, comes back down, and now it's at y equals 0. For this problem, I don't care about the distance it travels up and then the distance it travels down. I'm just talking about in terms of displacement, net displacement. We talked about that at the very beginning, like the very first video. Okay, so I don't care about it going up and down, I just care about its displacement. When it's in free fall, it starts here, 500 meters, it ends on the ground, 0 meters, right? I like the ground to be 0 meters. So its total displacement while it's in free fall is negative 500 meters. Okay, final minus initial, negative 500 meters. So I'm going to use that along with the initial velocity, right? Again, I don't care that it's going up and it's coming back down. I don't care about that part of the trajectory because I know what the velocity is when it started free fall. I know the displacement of it while it's in free fall. Free fall acceleration is g in the negative y direction. So I can use this to solve for T2. I'm calling T2 the time that the rocket's in free fall. Plug everything in. I got a quadratic. It looks nice, but it's still not factorable, right? So I'm stuck with using the quadratic formula. Plug everything in. Again, I'm going to get a positive time and a negative time in these types of situations. Pick the positive value, T2. I'm going to add that to T1. 24.6 seconds plus 10 seconds. The total time the rocket's in the air while it's burning fuel, while it's in free fall. 34.6 seconds total. All right. So I say try option 2. What's option 2? Option 2 is option 2 from this problem. Okay. Because check it out. Just like the rocket runs out of fuel right here, but it's still got a velocity in the positive y direction. What's it do? It goes up, reaches max height, comes back down at some location lower than its starting location. Okay. So this problem right here is everything from the rocket problem, just without this acceleration due to the fuel. All right. So try option 2 on your own. Find the speed or find the velocity that the rocket has right here. Find the velocity that the rocket has when it hits the ground, and then continue with option 2 to find T2. Find how long it's in free fall. You should get the same value here. Add it to 10 seconds, and you're good to go. Okay. So I'm going to pause it, and I think I just realized there's a problem at the end that I didn't do that was in the PowerPoint. So I'm going to get the notes for that real quick, and I'll upload this and contain that in a separate video. All right, thanks. Have a good one.